Okay, welcome to lecture here. We're continuing on with chapter 14. Okay, so we've been talking chapter 14, which has a lot of stuff in this chapter. So halfway through almost the chapter, I think. Uh, so last time we talked about, I think, we talked about weak bases and getting into the equilibrium calculations for those. Again, really kind of the same as any other equilibrium, except because it's a base, you do get the hydroxide concentration, and that's going to be what X equals. And then that allows you to get the POH first, and then you could get the pH after that. Um, we also talked about salts. So salts, right, are ionic compounds that are really a result of the reaction of an acid and base. So typically, when you react an acid and base, you do get a salt plus water, and that salt, in certain cases, has the tendency to continue to react through a reaction which is referred to as a hydrolysis reaction. And what that basically means is the salt, after it's sort of formed as a result of that reaction between an acid and a base, possibly can react with water. And in that reaction with water, which is the hydrolysis reaction, it may be able to produce H plus or H3O plus. It may be able to produce OH minus. And that gives us rise to what are sometimes referred to as acidic salts, basic salts. And there are some salts which are neutral salts. And the idea behind that is sort of that basic relationship that we talked about with acids and bases and their conjugate partners. So anything that comes from a strong acid or a strong base, its conjugate partner will be relatively weak. So typically, salts that are generated from a strong acid or a strong base will be relatively weak. And what that means is they will not continue to react with water. And again, we would expect the pH in that case really to be pH is 7, because there's no more reaction with water, which means essentially what you're left with is a salt and water at that point. No real generation of any H plus or OH minus. So we would expect the solution to be neutral or a pH of 7. If the salt reacts with water in the sense of being a base, it will accept the H plus from water. When it accepts the H plus from water, it will then produce hydroxide, OH minus. And because we're now producing some free hydroxide in that solution, the hydroxide concentration should go up, the pH should go up, and we would expect, again, the solution to be basic in that particular case. And we do have some salts that are basically derived from a weak base, and their conjugate acid part, which is the salt, has the ability to react with water, and it will react with water as an acid. So in that case, it's going to donate the H plus from the salt to water. When it does so, it produces H3O plus. And because we're now producing a lot of free H3O plus in that solution, we would expect the pH to start to go down because the H plus concentration is increasing, and we would expect the solution to be acidic in that case. So as we talked about last time, and we did some examples and some calculations, very, very common in sort of hydrolysis problems, you are given the wrong sort of K value. So you're oftentimes given the Ka value when you need the Kb, and vice versa. So definitely in that situation, we do need to use that relationship that we saw, that the Kw equals Ka times Kb. That allows you to kind of quickly switch around and figure out the Ka value if you need it, or the Kb value if you need it. Using Kw, that's 1 times 10 to minus 14. Also, it's important, as we talked about, to make sure that you can sort of correctly write those equations because it does give you a lot of information. It does help you understand what your numbers should be or your answers should be when you do those calculations. Any questions on any of that stuff that I think we talked about towards the end? We also talked about Lewis acids and bases. A Lewis acid is a electron pair acceptor. A Lewis base is an electron pair donator. So that's again another sort of definition of acid and base. And as I mentioned last time, we will see Lewis bases again in a later chapter come up a lot. Any questions on any of that stuff there that we talked about? Okay, so I think where we left off was here, and we're going to talk now about polyprotic acids. So polyprotic acids basically means that the acid has the ability to lose more than one H plus or give away more than one H plus. And when that happens, or when they do lose an H plus, as we talked about a little bit when we were talking about Bronsted-Lowry acid and bases, the H pluses do come off basically one at a time. They come off one at a time, and that's why when we talk about acid conjugate base pairs or base conjugate acid pairs, the only difference there is really one H plus. So it does just come off one at a time. So if we take something like our phosphoric acid, which is the first one in that list, the first step that will sort of happen is the H3PO4 will drop off that first hydrogen and form H2PO4 minus. And then the next step that will happen is that H2PO4 minus will then drop off the second hydrogen and leave us with HPO4 2 minus. And then the third step that will happen is that last guy there, HPO4 2 minus, will then drop off that last H plus. And we get PO4 3 minus. So it really is sort of a stepwise dissociation when each of the hydrogens come off. They're all actually equilibrium constants or expressions or reactions. So for each of the steps, we could have what is sometimes referred to as a Ka1 for that first H that comes off, a Ka2 value, and a Ka3 value. A couple of things, if we do look at the numbers, and what we might anticipate is it is much easier to remove that first hydrogen, that first H plus, than it is the second one. For a couple of reasons, after we remove the first H plus, we're now left with something here that has a negative charge, and you're trying to remove something that's positive. It's going to hold it tighter, so it makes it much harder to remove, and it even makes it even harder to remove as you get to that third H plus that comes off. So it's much easier to remove that first H plus than the second or even the third. And we see that really displayed here in our K values when we look at the 3 K values for phosphoric acid. The first one there is, I believe, to the -3. The next one is like to the -8 and -13 on the third one. So as we kind of go downward here in terms of each of the H's coming off, the Ka value gets smaller and smaller. So when we have a small Ka value, right, that means we mainly have reactants. So as we get to the third one, we're mainly going to have the reactant guy. The second one, also mainly the reactant guy. The first one is the largest, so we expect more of the product here to come off. So that's the trend that we see for all these things. This carbonic acid has 2 hydrogens to come off. An acid that has 1 hydrogen that will come off, sometimes referred to as being monoprotic, for one acid, 1 H plus. The guy that has 2 is what is referred to as being diprotic. Our one that has 3 that comes off is sometimes referred to as being triprotic or polyprotic, basically. And these are generic sort of formulas. We saw HA earlier. If you have a diprotic ion, you don't really have a form like you use H2A, H3A. The important thing when you remember that is that the charge on A changes. The A here is -1. A here is -2. A here is -3 in terms of the charge, kind of like what we have here with phosphate, -3 overall. Although we don't sort of think of this as a stepwise sort of dissociation, that's because what we think about when we look at something like this is we add up all these reactions together. What ends up happening is, this guy cancels, this guy cancels, and what we're left with is sort of what most people sort of visualize as the overall reaction. H3PO4 basically will give you your 3H pluses and your phosphate. So although most people think about the overall reaction here, and that's why a lot of times, sometimes people will think, all of them just pop off at once. They actually don't. Again, they do it in a stepwise fashion, and each one is an equilibrium expression, and each one will happen one after the other, much harder after that first one comes off. Any questions on that there? So we'll come back to that real quick. Let's take a look at an actual calculation here. So let's say we wanted to do this calculation where we pretty much want to calculate everything. So we want to calculate the pH, the concentration of phosphoric acid, the concentration of H2PO4 minus, HPO42 minus, PO3, PO43 minus, H plus of a 5 molar phosphoric acid solution. So let's go through this calculation to see how it works. So the first thing that's going to happen really is the first dissociation. So let's get somewhere to write here. So the first thing that will happen is the first hydrogen will come off, and this is the K value here that goes with that first hydrogen that will come off. All right, so it would be H3PO4 going to drop off again, just the one hydrogen. And again, this is going to be Ka1, which again holds 7.5 to the -3. All right, so because it is an equilibrium, we need to do an ice table. So we would do our ice table here. We have 5 molar. We would have 0 and 0 going on. Change like normal here would be -x plus x plus x. That means at equilibrium, 5 minus x, x, and x in this case. So the ice table, just like sort of a normal Ka table, we got our x's. We're going to do our normal thing here. We're going to put this into our Ka1 expression, and that is the concentration of H plus, H2PO4 minus, divided by our phosphoric acid, and that's going to equal, again, our Ka1 value. We're going to put our numbers in. That's going to give us x squared divided by 5.0 minus x will equal 7.5 times 10 to the -3. I'm going to assume that x is equal to 0 here. Give it a go. That gives me x squared over 5 equals 7.5 times 10 to the -3. So I'm going to multiply 5 to the other side. I'm also going to take the square root there. So 5 times 7.5 to the -3 and a square root of it. Going to give me something, we'll call it 0.194. We do want to check it like normal. So we want to take that divided by 5 and times it by 100. And we get something like 3.8% on the check. So the check is good. So now we have an X value, and from our very first table, we actually have a bunch of answers sort of given to us. We see that the H plus concentration from the table equals X, and that means it would equal 0.194 molar. We also see that the H2PO4 minus concentration also equals X, which would be 0.194 molar. We also know that the phosphoric acid would equal 5 minus X, which would be 5 minus 0.194, looks like 4.81 molar. So from this very first dissociation of an H plus in this weak acid here, if we go back to what we're looking for, we have now identified this concentration, and this concentration. But we still have a couple other concentrations that we're looking for. So that is going to require us to go to the next dissociation that we have going on there and see if we could get those concentrations. So that would be the next step. So the next step would be that the second H would come off. So remember, when the second H comes off, what we have going is H2PO4 minus. We'll then lose that second H plus and leave us with HPO4 2 minus. And this would be our Ka2 value that we saw there, which was 6.2 times 10 to the minus 8. So here we want to do, again, another ice table. So we would have initially here, and you may ask, where does our initial concentrations come from? So our initial concentrations at this point would actually come from our previous steps equilibrium concentrations. So from the previous step, we know that H2PO4 minus is 0.194. So that would be where we would get that number from the previous step. In addition, from the previous step, we actually do have some H plus that was produced. Also the exact same number there, 0.194. And nothing of this guy. So these first two guys here are going to be the previous equilibrium concentrations carried over to our new ice table. And the change part in the rest of the table will be pretty much the same, minus X, and plus X. This will then give us at equilibrium 0.194 minus X, 0.194. Remember, this is plus X on this side, and that is X. Any questions on this ice table? So we're sort of carrying over the previous equilibrium as our initial starting amounts in our next table. Any questions on that? So we're going to then finish this like normal. We're going to put this into our Ka2 expression, which is our products over our reactants. And again, that will equal the Ka2 value of 6.2 times 10 to the minus 8. I will put in the values here. So that will give me 0.194 plus X times X divided by 0.194 minus X, going to equal 6.2 times 10 to the minus 8. We've had good luck so far, so let's try it again. We're going to assume that X is equal to 0. Remember, again, you can't get rid of all the X's. So in this case, it is just the X's we're going to add to a number or subtract from a number. So it would be those two X's. That would give me 0.194 times X divided by 0.194 equals 6.2 times 10 to the minus 8. I think I could do that math. That gives me an X is equal to 6.2 times 10 to the minus 8 in that case. Here, like normal, again, we made the assumption, so we do want to make sure that we check it. We're going to take 6.2 to the minus 8. We're going to divide it by 0.194, and we're going to times it by 100. And we are nowhere even near 1%, so it's less than 1%. So the check is good in this particular case. At this point, what we got going now is we can basically figure out a couple more concentrations. We now can see from here that the HPO4 2- concentration equals X, and that gives us a concentration of 6.2 times 10 to the minus 8 molar. Now, let's talk about what happens with our H plus concentration. Our H plus concentration would be 0.194 plus X, which if you do that, you still get 0.194 molar. Has not changed. And if you do the same thing for our H2PO4 minus, 0.194 minus X, you will also see it has not changed either. So these guys really has not changed here when our second hydrogen came off. So if we go back to our goal here, we have now just found this guy. So we've found pretty much everybody. The one last guy that we are still looking for is the phosphate concentration. And that's going to require us to go all the way to the third hydrogen coming off and our Ka3 value of 4.8 times 10 to the minus 13. So let us continue on there. First off, any questions though on the second step? Okay, so because we were asked to get to the phosphate concentration, that is going to require us to get to the third step to take off the third hydrogen there. And that third hydrogen is going to come off of this guy here. And because it's the third hydrogen, we'll use the Ka3 value of 4.8 times 10 to the minus 13. Just like we did previously, our initial concentrations are going to come from the equilibrium values of the previous table. So that's where we're going to get our equilibrium guys, our initial guys, pulling over our equilibrium concentrations. So in this case, we have 6.2 to the minus 8. Again, we still have H plus hanging around, and that is still 0.194, and this is 0. So again, we carried over our numbers from the previous step there to our new ice table to kind of start as our initial. The rest of the table, again, going to look very similar to all the other tables that we've done. We're going to do our X's. So the change here going to be minus X plus X plus X. This is going to get us to 6.2 times 10 to the minus 8 minus X, 0.194 plus X, and X. So again, very similar to the previous two tables that we did. Just like the previous two tables, at this point, we're going to put this into our Ka3 expression, which is the H plus concentration times the PO4 3 minus concentration divided by our HPO4 2 minus. And again, since we're on the third one, we are going to get it equal to our third Ka value of 4.8 times 10 to the minus 13. We're going to put all of our guys into this expression like normal. So we're going to go with 0.194 plus X times X divided by 6.2 times 10 to the minus 8 minus x. And again, going to equal our Ka3 value here. Might as well continue our assumption here since we've been good so far on this one. We're going to assume x is equal to 0. Again, our x's that we're adding are our x's that we're subtracting from a number. That will give us 0.194 times x divided by 6.2 times 10 to the minus 8, equaling 4.8 times 10 to the minus 13. We're going to multiply the 6.2 to the other side and also divide by 0.194. So if we do that and divide by 0.194, we do get something like an x value of 1.5 times 10 to the minus 19. Again, we should probably check that. So we'll divide it by 1.94 and see how we do. I think we should be okay at this point, but 0.194. We are nowhere near 1%. If you want to divide it by both numbers, you should also be okay. So if we divided it by 1.5 to the minus 19, divided by 6.2 to the minus 8 times 100, you're good. Either number that you check, you're nowhere near 1%, so the check is good. So what this tells us now is we can finally get our phosphate concentration, which in this case would equal x, and that is 1.5 times 10 to the minus 19 molar. Now, in terms of our H plus concentration, if you took H plus, which is 0.194, and you added it to X, you would again still get 0.194 molar. And if you did the same thing for our HPO4 2 minus and took the 6.2 times 10 to the minus 8 minus our 1.5 times 10 to the minus 19, you are still going to get the same number that you had previously. And we will end up with the same value, which is 6.2 times 10 to the minus 8. Question on this third table here, where we got any of those things. So let's talk about what we're actually seeing here as we've done this calculation with real numbers and get some values. Let's actually talk about what we are seeing here. If we go back to what we were looking for, we have now found this last one. We could also now find the pH. So to find the pH, pH is equal to minus the log of the H plus concentration. So let's take a look at what happened with the H plus concentration as we went from each of the steps, as we lost each of the hydrogens. When the first hydrogen came off, we ended up with a concentration of 0.194 molar. Then the second hydrogen came off, and we ended up with an H plus concentration of 0.194 molar. It absolutely did not change, really. When the third hydrogen came off, we ended up with a concentration of H plus of 0.194 molar. It really didn't change. In reality, it did change. So, for example, here on the third one, it changed by 1.5 times 10 to the minus 19. That's like 0.18 zeros and a 1. So ultimately, not very much came off at all. So what we see in terms of the H plus is what we talked about at the beginning. A vast majority of all of the H plus that's going to come off in this triprotic acid comes off at the very first step. That very first step is where we get rid of all of the H plus. Does a little bit of it come off on the second one? It does, like 6.2 times 10 to the minus 8 in this case. Very, very small amount. Does some of it come off on the third step? It does. 1.5 times 10 to the minus 19. But for the most part, the concentration of H plus that comes off does result from that very first hydrogen that comes off of a diprotic acid, a polyprotic acid. So in problems where you're maybe not interested in everybody like we were here, maybe in a problem that involves a diprotic acid or a polyprotic acid, and really the only thing you're interested in is the pH, you probably can, in most cases, just do the first step here and use that H plus concentration to figure out the pH. That is because, as you can see in this calculation, we do not lose a lot of it anymore in the second one or the third one. It's a very small amount that comes off. Again, it gets very harder to lose that additional H plus every time you take one off. And we see that here with the numbers. So if it was a problem where you weren't asked to solve for everything, you could probably safely just go into the pH equation after you do that first hydrogen that comes off. So in our case, I think it was 1.194, which would give us a pH in this case of 0.71, which is definitely acidic, which is good because it's an acid. So when you're dealing with polyprotic acids, if it's really just a pH type situation, and that's kind of really all you're trying to calculate, like I said, probably 9 times out of 10, maybe even more than that, if you just do the first hydrogen that comes off and get the H plus concentration, you probably will be good in terms of your pH. If it's a problem like this where it wants everybody's concentration, it does require you really to do each of the steps. And again, the real purpose of us having to do the second step was it's the only way we really could get to this guy's concentration. The reason we had to kind of do the third step, it was really the only way to get to this guy's concentration. So again, if we weren't asked those things and just the pH, pretty safe to probably do it off of the first hydrogen that comes off and get the pH from that. Question on polyprotic acids, how to do those problems, how to calculate them. Any questions on any of that? Okay, so that is polyprotic acids. So the next thing we're going to talk about, which is a really sort of big topic here in this class, is what's referred to as the common ion effect. And we're now getting into sort of the difficult part of some of these topics, the part that gives people a lot of trouble, you know, in this class. And this is really the part where you do have to really understand what is going on to be able to kind of do the math correctly. As we go through what we're going to be talking about now, which is buffers and then into titrations. Again, there's a lot of places in here where you may think it's okay to do a certain sort of math calculation. But if you truly understand what is happening in the problem, you would see that you probably shouldn't do the math. So again, these are definitely the areas here in this chapter and the topics that we're getting into that you really don't want to go just like on autopilot, try to just go, okay, I'm going to do this, this, this. You really do have to sort of think about what's happening here so that you can really do the right math. And it's very common that people just kind of go autopilot and sort of go, okay, cool, I got 2 numbers. This formula needs 2 numbers. I'm just going to throw it in there and go for hope for the best. So let's talk about really what the common ion effect is. The common ion effect is the idea where we have a shift in equilibrium that's caused by, the name implies, a common ion. And the presence of this common ion will essentially suppress the ionization of a weak acid or weak base. So the presence of a common ion will essentially cause the weak acid or weak base to stay together. It won't allow it to break apart and basically produce H plus or OH minus in the case of a base. So for example, if we look at If we look at acetic acid, which is this guy. So acetic acid is a weak acid. And if we have just acetic acid by itself, it's going to break apart into H plus and acetate. And this would be the normal equilibrium that would happen if we just had acetic acid by itself. But now, if we take acetic acid and we mix it with some, say, sodium acetate. So if we take that acetic acid and then mix it with some sodium acetate. What's going to happen here? So let's think about what sodium acetate is. Sodium acetate is a salt. And when it is in solution, it's going to break apart into two things. It's going to 100% break apart into sodium ions. And it's going to break apart into acetate ions. So if you take your acetic acid, you dump some sodium acetate in there with it, you now have a big source of sodium ions and a big source of acetate ions. Now, in the beaker, if you visualize it, I'll draw a very wide beaker here. When you dump both of those things in, the acetic acid and the sodium acetate in, the only thing that's going to set up an equilibrium in there is the acetic acid. So the acetic acid is really the only thing that's going to, in that solution, set up that equilibrium. The sodium acetate will not set up an equilibrium. It's a one-way street to breaking apart into ions. So essentially what you did is when you add the sodium acetate to this solution, you now have your equilibrium that's set up, and now you have some sodium ions in there, and you have some acetate ions in there. So what's going to happen, if you think about it, is our good friend Le Chatelier's principle will tell us that basically the acetate that has been added is our common ion, and that essentially is going to add more acetate. And if we add more acetate to that equilibrium that's been set up, Le Chatelier's principle should say that it should shift the equilibrium to the left. And if it shifts the equilibrium to the left, what that means is the acetic acid that's in equilibrium will basically remain together. And as it shifts to the left, that also means that the concentration of H plus will probably go down, right? Because in order to make the reaction go to the left, our two products here has to react. That's going to lower the H plus concentration, keeping the weak acid together. And what is that going to do to the pH? Well, if I lower the H plus concentration, that means that technically the OH minus concentration should go up, and so should the pH should go up. Will it go up to basic? No, but it will rise. So in comparison of the pH between acetic acid by itself to acetic acid with some sodium acetate in there, we would expect the pH to be higher in this guy, again, because we have less H plus that's in the solution because it's basically staying together. So the common ion will keep the weak acid from breaking apart as much. The end result of that is it will lower the amount of free H plus in the solution. And remember that the pH is really determined by how much free H plus is in that solution. So if we lower the H plus concentration, we would expect the pH to be higher than it would be if we had the weak acid alone. with the weak acid alone, is able to set up that equilibrium, is able to break apart however many H pluses it can. But with that common ion there, it's going to push everybody back the other way and kind of keep everybody together. Any questions on that? Okay. So let's take a look at some calculations here that sort of involve this, and we'll talk about how to do them. So why don't we start with A? Why don't you start with A first? What is the pH of a 0.2 molar acetic acid solution? Ka value for acetic acid is down here. So take a couple minutes here and just do part A, and then we'll talk about it, and then we'll do part B in just a second. So take a little bit of time and work on that one and see what you come up with. Again, we're looking for the pH of just acetic acid by itself here. And to give you an idea, obviously it should just be a weak acid type problem. Okay, so let's take a look here, see how we're doing. So looking at part A, like I mentioned before, it really is just a weak acid. So all we have in there is just the weak acid, which is acetic acid. And we have the Ka value given to us. So we're just going to basically treat this like normal. So we have 0.2 molar, it looks like. So we're going to take our weak acid, which is our acetic acid here. It's going to break apart. And this would be a Ka value of 1.8 times 10 to the minus 5, if I got that right. Yes. All right, so like normal, this is just a regular old Ka value like we've been doing here. So we're going to start with 0.2. It's going to be 0 and 0. Change going to be minus x plus x plus x. Going to give us at equilibrium 0.2 minus x, x, and x. Any question on the ice table? So just like kind of the ice tables we've done previously for weak acid. At this point, just like we've kind of normally done here, we're going to go into our Ka expression, which is our products divided by our reactants. And that will equal our 1.8 times 10 to the minus 5. I'm going to put my values in there. That's going to give me x squared divided by 0.2 minus x equals 1.8 times 10 to the minus 5. Been having good luck so far. Might as well continue and try. So we're going to assume that x is equal to 0 here. And if we do that, that will give us x squared divided by 0.2 equals 1.8 times 10 to the minus 5. We're going to multiply the 0.2 to the other side. We're also going to take a square root of it. So let's see here, 0.2 times 1.8 to the minus 5. A little square root action. And that's going to give us an x value of 0.00. We'll call it 190. We do want to check it. So we're going to take that and divide it by 0.2. We're going to times it by 100. And it looks like we're something like 0.94%. So the check should be good here. That is going to be our H plus concentration, as we can see from our table here. So the concentration of H plus will equal X, which in this case is 0.00190 molar. That means that our opening pH here for our acetic acid solution would be minus the log of 0.00190. That should give us 2.72, I believe. Yes, it is. And again, that is an acidic pH, which does make sense since this is an acid. Any questions on any of those steps? Again, pretty identical to the Ka type problems that we did earlier on in this chapter. Any questions on any of those steps where we got any of the numbers or any of those things? Okay. So what we're going to look at now is part B of this question. And if we go back and look at part B, it is a little different. We are still using the same solution. So we're still using the same 0.2 molar acetic acid solution. But in addition, we're going to dump into that beaker, whatever it may be, flask, also 0.3 molar sodium acetate. So again, kind of back to that drawing I did previously. When we dump both of those things into this solution, it is only the acetic acid that will set up that equilibrium. Again, it's a weak acid, so it is only that acetic acid that will be able to set up that equilibrium. When we dump the sodium acetate in there, as I drew a second ago or earlier, it is really going to break apart 100% because, again, it is a strong electrolyte, basically. So it will one-way street 100% break apart into sodium ions and acetate ions. So by dumping that in with our acetic acid, again, we can look at that really as a source of sodium ions and a source of acetate ions. If I have an extra zero. And we're going to get that common ion effect as we talked about previously. So let's take a look at how the calculation will sort of be different here when we have part B. So looking at part B now, as I just drew and as I just was talking about in part B, we are still going to have the same equilibrium. So again, it's only going to be our acetic acid here that's going to set up that equilibrium. And because it is still acetic acid that's setting up that equilibrium, our Ka value will still be the same. So we're still using the same Ka value. So let's talk about the ice table here. So initially, we have our 0.2 molar of our acetic acid. We initially have 0 here, but the difference is from where this differs from the part A is we actually do have some acetate available to us initially. And that is going to be because this is 0.3 molar. The sodium would be 0.3 molar as it's a one-to-one relationship. And the acetate that you dumped in there would also be 0.3 molar as it's a one-to-one relationship. So when people do these sort of common ion problems, the part that they always screw up on, I think is the right way to word that there, is that they go, oh, I've been doing 0 forever. This should be 0. And it's really not 0 in this case. Again, it's not going to be 0 because you have added some sodium acetate to that, which is a source of acetate. And that means that you're actually going to be starting with a number here. So that is where I would say 99% of the time people screw up on is they will zero out that when we're doing a common ion. Why is that important if you zero that out? If you ended up zeroing it out, you're pretty much redoing this problem here, which is going to give you obviously the same answer. So you want to make sure if you do have that common ion that you should have a starting amount of that common ion on the initial part of the table. And again, that is a very, very super common error that people make all the time. The rest of the table after that point, once you hopefully get over that hurdle there, is going to be the same. We're going to go minus x, and plus x. That means at equilibrium, 0.2 minus x, and again, 0.3. Other common mistake, so used to the minuses at this point, but again, it is plus x on this side. So that's another very common sort of error that people make is they subtract on the back end there instead of adding. Any questions on the ice table here with the common ion that's present and how it's different from what we were just looking at? Okay, so at this point, it really is very similar sort of end result here in terms of the calculation. We're going to go into our Ka expression like normal. Also, sometimes people struggle with, I should be using the same Ka, and you should. Again, the acetic acid in this example is the only one that's going to set up that equilibrium. So we're going to put our numbers in like we've done before. So we're going to have x times 0.3 plus x divided by 0.2 minus x. And that will give us 1.8 times 10 to the minus 5. Might as well continue on my streak of assumptions here since we've been doing good so far. So we will once again assume that X is equal to 0 here. Again, just the ones we're adding and subtracting from are the ones we're going to do that to. That gives us X times 0.3 divided by 0.2 equals 1.8 times 10 to the minus 5. We're going to multiply the 0.2 to the other side and also divide, looks like by the 0.3. So 0.2 times 1.8 to the minus 5 divided by 0.3 gives us something like 1.2 to the minus 5 on the X. X is equal to 1.2 times 10 to the minus 5. Again, we do want to check it. So we'll take that number divided by 0.3, for example, times it by 100, and you're like 0.004%. So, your check is good here on that. And again, a reminder, 0.3 times 100 is how we check it. So since that is good, that will give us our H plus concentration. So the concentration of H plus in this case does equal X, which equals 1.2 times 10 to the minus 5 molar. That's all we need for our pH here, minus the log of the H plus, minus the log of 1.2 times 10 to the minus 5. And that gives us a pH of this solution of 4.92. Any question on that calculation there? Okay, so what does this mean? Let's take a look and see what this means. Well, this was our common ion here type problem. This was our no common ion. What do we see in terms of the H plus concentration and the pH? Well, without the common ion there, we had an H plus concentration of 0.0019 and a pH of 2.72. By the presence of that common ion, which causes this equilibrium to shift to the left, we ended up with a concentration of H plus of 1.2 times 10 to the minus 5, a much smaller amount of free H plus. The result of that is, as we were talking about before, we see that the pH then went up from comparison of the weak acid by itself to the weak acid and the common ion being present. So these are things that you do want to think about. If for some reason you did this calculation and you got a pH that was less than the weak acid by itself, something definitely went wrong in your calculation. So this is what we would expect to happen here because of that common ion effect, causing the equilibrium to shift to the left, keeping the H plus on the acid, not allowing as much free H plus from floating around the solution. And again, we would expect that the pH would rise in comparison to the acid by itself. Any questions on that there? Now, you definitely could do this type of problem, this common ion type of problem, like we just did, doing an ice table. Again, the key part is if it is a common ion, you need to have something here in terms of concentration and not 0. But there is also another way that you can approach these sort of common ion problems, which will allow you maybe not to have to do the ice table. And let's talk about that. So in problems where it involves the common ion effect, we usually get starting concentrations of the weak acid and its salt, as long as they're kind of reasonably high, kind of 0.1 or above, we could almost neglect everything that's going on. And essentially what happens is the initial concentration of those guys actually end up being the equilibrium concentrations of those guys. So what I mean by that, if we look back at our problem we just did, although we did not calculate what the equilibrium concentration of our weak acid was, if I take 0.2 minus 1.2 times 10 to the minus 5, which is our X value here, I will still end up with 0.2 molar. If I take my acetate and I take 0.3 plus 1.25 to the minus 5, I will still end up with pretty much 0.3 molar. So what they are saying is essentially when you have this common ion, because it doesn't allow that acid to break apart as much as it should, what you start with in terms of the initial concentration, a lot of times will end up the same at equilibrium. So you won't have a tremendous difference that's going to occur between initial concentrations and equilibrium concentrations. And that's important because it does allow you to use actually a formula instead of an ice table to solve for it. And you can use this formula here, which if we have a mixture of a weak acid and sort of a common ion, we could use, and everything on the left is really just sort of how it gets derived. This is what is known as the Henderson-Hasselbalch equation, which is the pH is equal to the pKa value plus the log of the conjugate base divided by the acid. To solve for the pKa value, it is the minus the log of the Ka value. So in a common ion problem, and later in this chapter, not too long after this, these are really buffer problems. You can use the Henderson-Hasselbalch equation to calculate the pH of a solution. This is usually what people will use for the Henderson-Hasselbalch equation. I personally also would recommend using the pH equals to pKa plus the log of the base over the acid. There is a version of sort of the Henderson-Hasselbalch equation that doesn't calculate pH, but calculates pOH. And I will put that up here, but I personally think it's not very useful, kind of. And I'll tell you why in just a second. So you can actually calculate the pOH is equal to the pKb plus the log of the acid over the base. So it's a little bit different. First off, it's a pKb here, which is found the same way. pKb is minus the log of the Kb value. And it is not base over acid, it is acid over base. So you could use these relationships here, but the purpose of this equation here, again, I personally don't see the benefit because usually in a problem, you're asked to solve for the pH. So why you wouldn't just go right into this equation here and get the pH rather than go here, get the pOH and still have to subtract 14. It doesn't really make a lot of sense to kind of use it a lot of the times, but you will see perhaps this guy pop up somewhere. But it's important to remember that this one doesn't give you the pH, it gives you the pOH, and it is acid over base rather than base over acid, which is the Henderson-Hasselbalch equation. So personally, I would use this one all the time, the Henderson-Hasselbalch, because in most cases, that is what you're looking for, the pH, not the pOH. Some people like to use this one when you get into sort of basic buffers and stuff like that. But again, you're still usually asked for the pH, which means you still have to do the subtraction. So personally, I would stick with these two here, the Henderson-Hasselbalch, the pH and the pKa value there. And that will usually get you to the right one. You can use it for acidic solutions, basic solutions, neutral. It doesn't really matter. You can use it for any sort of situation that's a common ion. But while we did talk about pKb, there is a nice relationship that might be helpful as well. And that is if you take the pKa value and you take the pKb value, it equals 14. So if you add them together, it does equal 14. So sometimes that's a quick way. If you maybe need a pKa value, but you have only a pKb value, you could kind of calculate it really quickly. So there's a few different equations here. personally, again, like I said, Henderson-Hasselbalch pH equals a pKa plus the log of the base over the acid, probably the way to go in most cases, because usually you are looking for the pH. So what does this equation allow us to do? Well, if we look at part B, the problem we just did, which was obviously this one here. If we now approach part B the exact same way, but using the Henderson-Hasselbalch equation, let's see how that would look. So redoing part B here using our Henderson-Hasselbalch equation, which again is the pH is equal to the pKa plus the log of the base over the acid, where the pKa value is minus the log of the Ka. So just to remind everybody what we had going, we had 0.2 molar acetic acid. We had 0.3 molar sodium acetate. Again, common ion problem. And we had a Ka value that was 1.8 times 10 to the minus 5. So we could calculate the pKa value by taking minus the log of 1.8 times 10 to the minus 5. Going to give you 4.74 as our pKa value. And that means that we could go into the Henderson-Hasselbalch equation, pH equals 4.74 plus the log. Also troublesome for some people, acid and base. Obviously, this is the acid in this case. Usually the one that has one less hydrogen is like the base. So we do want to go base on top. So that is 0.3 divided by acid on the bottom, 0.2. And if you do that, 0.3 divided by 0.2, take a log of it and add it to 4.74. We will get 4.92. And if you look back at what we got previously when we did the ice table, we got 4.92. You get exactly the same answer. This is sort of a time saver, but it is also troublesome for a lot of people because they're like, I got this equation. I'm just going to use it in every situation. You should not use it in every situation. It really should only be used, the Henderson-Hasselbalch equation, in a common ion situation, which is really a buffer situation that we'll talk about. So it's really a buffer situation is the only place that you should use that. You should not use it in other places. And this is the place where a lot of people will mess up because they will go, cool, I got two numbers. I could put two numbers into my Henderson-Hasselbalch equation and get the pH, and it's not what you should be doing. How can you tell which one is the acid and which one's the base? So there's really a couple ways. So for example, if in this problem, one sort of simple-ish sort of way is if you identify what the Ka value is for, that is for the weak acid. So you know this guy would be the weak acid. Otherwise, an acid typically is something that will donate an H+, right? So it donates to H+. And that means that the acid should have more H pluses and the base will have less H plus. So in this situation, as you can see, this is acetate, 1 H plus less. In addition, typically the base will have like a spectator ion involved, like a potassium, a sodium, lithium. It'll have some type of spectator ion present, like we see here, sodium. So that's a good way to kind of sort of identify it. Again, the acid usually will have more H plus, the base will have less H plus, and the conjugate base will have, again, like a spectator ion. So remember when it donates it and it becomes the conjugate base. So really what we're looking at is this relationship, the acid to its conjugate base. And the conjugate base will this. So it has usually one less H plus, the conjugate base. The acid has one more H plus. we're going to talk about buffers next. So we'll talk about what a buffer is in just a second, but that's basically it here. It will not necessarily indicate in a problem that it is a common ion effect. It will not also sometimes indicate in a problem, as we're going to talk about buffers next, that it's a buffer situation. Again, these are the things that you need to kind of know. And again, these are the things that give people sometimes a difficult situation because they can't recognize these things. So this is what we were talking about earlier, that it's super important to sort of understand what's happening in the problem so that you can kind of apply the right sort of calculation. And again, that's what gives people really the hardest time in this sort of section of the class here, is you really do have to sort of understand, looking at a problem, what is actually happening. Because in blinking lights, they're not going to tell you, hey, this is a buffer problem, or this is a common ion problem, you should be doing this. They just sort of assume in problems usually that you understand, oh, I got a weak acid and I got like a conjugate base sort of situation happening. That's ultimately a buffer, as we'll talk about, or a common ion type situation. So it's really, like I said before, the conceptual part of it here in this part of the chapter is super important to really understand. You definitely just don't want to go on autopilot. You want to take a couple of minutes or so, or a little bit of time, and sort of think about what you're dealing with, because they oftentimes won't just straight out kind of tell you. All right, so why don't you try one here and see what you come up with. What is the pH of a solution that is 0.3 molar formic and 0.52 molar potassium formate? Ka value is 1.7 times 10 to minus 4. Okay, so let us take a look here. So we want the pH of the solution containing zero point 0.3 molar HCOOH, which is formic acid, by the way, and 0.52 molar potassium formate. And so our earlier question was, will they tell you if this is a common ion or a buffer or whatever it is? And clearly, a question like this, they do not tell you. So what you need to be able to recognize is that these two things here, they do look related to each other. And we have a Ka value, which means one of these guys probably should be an acid. And again, as I mentioned before, the acid will have the extra hydrogen. The conjugate base will have one less. And again, that's that acid on one side to conjugate base relationship is difference of one H plus less. So we have that difference here. So we know that this guy is our conjugate base. The HCOOH is our weak acid. That's a common ion. Again, just to show you here, what's going to happen is this guy is going to set up the equilibrium. And what's going to happen with our HCOOK is it's going to break apart into HCCO minus plus K plus. This right here going to be our common ion. So you have two ways to solve this. Either way is perfectly fine. It really is just sort of a preference. So since I sort of started it here, let me just kind of show you the start of one way here, which is the ice table way. Again, in the ice table approach, you would go with 0.3 there. This would be 0. And again, because it's a common ion, we would have an initial concentration here of our common ion coming from this guy up here. Now, the rest of it would be the same, minus x plus x plus x, going to get you at equilibrium 0.3 minus x, x, and 0.52 plus x. If you were going to finish it out through the ice table way, it would go into your Ka expression like we've done before. And again, that will equal our Ka value of 1.7 times 10 to the minus 4. That will give you x times 0.52 plus x divided by 0.3 minus x. Again, that will equal our 1.7. At this point, you could do your assumption and solve for x. I'm not going to finish it out because the alternative approach to this would be, if you recognize that right off the bat, you don't have to do any of this move. You could just go right into the Henderson-Hasselbalch equation. pKa plus the log of the base over the acid. Here we do need to figure out the pKa value. That would be minus the log of our Ka, which would be minus the log of 1.7 times 10 to the minus 4. And that would get us, what we got there, 1.7 to the minus 4. 3.77, we'll call it. Which means that the pH here would be 3.77 plus the log. Now that we've identified which one is the base, we should go with 0.52 over the acid 0.3. That's going to give us 0.52 divided by 0.3. We're going to take a log of that, and we're going to add that to 3.77, going to give us a pH of 4.01. I stopped up here, but if you continued on and solved for x and you calculate the pH, you will get 4.01 as well. So again, if you made your assumption, solve for x, you'll get the H plus concentration and put it in there. You could absolutely do it either way. You could see that probably the Henderson-Hasselbalch way is a little bit quicker, a little bit easier. Honestly, a little less room for error because you probably will not forget this guy like most people will. They do the ice table, and probably a little less room for error. So If you could recognize it as a common ion, and again, this is really buffers, as we'll talk about next time, I would probably stick with the Henderson-Hasselbalch equation. If you can't or don't want to do it or don't want to take the risk of using the Henderson-Hasselbalch equation in the wrong situation, you could 100% always go ice table approach. So you do have a couple of options to do it. Again, one could be a little quicker in some cases, but they both should get you to the same end result as long as you do them correctly. And again, it really is a personal preference. You don't have to use Henderson-Hasselbalch, but again, it can be a pretty good time saver in a common ion type situation. Question on that there. Okay, we will stop there for today. We'll pick back up at lab about 11:30ish there. We'll talk about the next experiment, which is about pH and hydrolysis. So we'll talk about part 1 of that experiment, and we'll start working on it. All right, if you didn't put it here, please do so. I'll see everybody in about 20 minutes or so. Go stand up and stretch.